In this final lecture in week 2, we go back to energy units and conversions and talk a bit more about equivalence between different energy types. So go back to different energy units. I introduced last time the concept of TOE, ton of oil equivalents, megawatt hour or gigawatt hour or kilowatt hour and gigajoules, and they all are basically measurements of the same thing about energy. And here, if you want to go from ton of oil equivalent to megawatt hour and multiply by 11.63, 41.868 gigajoules per TOE and so on. The number you might be familiar with is 3.6 gigajoules per megawatt hour. That's 3.6 megajoules per kilowatt hour, or 3.6 kilojoules per watt hour. Here's a useful resource, the IEA unit converter. So you won't learn much, you won't get to do it yourself, but at least you'll have this resource where you can convert energy units like this. Here are some more complex energy units. I mentioned some non-standard energy units, including quads, calories, billions of oil equivalent, and so on, and here's a more complex. You obviously don't have to remember any of this, but here's a resource if you need to do any strange energy conversions. I introduced the concept of the calorific value. The calorific value is the energy content of fuels. The reason it's important to have the calorific value of different fuels is because we need to convert all of the physical or natural units of energy, which is, tons, cubic meters, liters, barrels, for example, into a common energy unit, so that we can compare the energy content of fuels, so we can create energy balances, compare trends, and so on, and compare different options. So the net calorific value, it's also known as the net heating value, expresses the heat obtained from 1 unit of that fuel when you combust it, when you fully combust it. But the concept of net calorific value means that you subtract the energy contained in the water vapor or the exhaust gas, because basically you don't get the full heat because there's some latent heat lost in the water vapor and exhaust gases. You don't really need to know that. Many of you probably know this much in much greater detail. And we measure calorific value in terms of the energy unit per physical unit. So that's the joules per kilogram, the kilowatt hours per litre, and many different sources have different types of units. And the thing about the calorific value is that they may vary significantly over time, from country to country, and between different products. So different ways, there are different methodologies of estimating those. That's because the quality of different products changes over time, the ways of producing them change over time. Different types of crude oil, for example, have different amounts of energy. Different grades of coal, natural gas have different energies. So those are standardized usually, and we get a calorific value for each country. By the way, this unit is also known as the energy density. So how much energy is contained in either a weight or a volume of a particular type of fuel. Here are some calorific values in terms of the net calorific value. Here, this is ton oil equivalent per ton and megajoule per ton of different sources. Here from crude oil to petroleum coke, and you can see that oil here has a higher calorific value than, say, coal. So coal contains more ash. Peat then has the lowest, and sod peat have the lowest calorific values because they contain more moisture and less carbon. They're less carbon dense. Electricity then. These are just simple conversion factors that we showed before. So 86 ton of oil equivalent per gigawatt hour, 3.6 terajoules per gigawatt hour. These are not calorific values, so electricity is already in an energy unit. Here are some more energy conversion factors. So if you're interested in the joules per kilogram of coal, here's a resource for that. Again, just a resource, nothing that you need to remember. What you really need to remember is how to use those, how to apply them, and I'll go through some examples there. So if we want one issue, if we have the energy density in terms of calorific value, say the joules per kilogram but we know the volume. We need to also know what the volume to weight is. So basically what the density of different fuels is. And that varies again with different types of fuels. So for example, there's in a cubic meter, that's 1,000 litres of diesel that weighs about between 830 to 860 kilograms. And that's something that we need in some of the calculations we'll be doing. Here are some more net calorific values of different fuels in terms of kilojoules per kilogram or joules per gram, million joules per million grams. And some sources and interesting readings. Some of you expressed interest in different ways of calculating orders of magnitude, things like that. And here are some links. Next, we'll go through some sample questions and I'll work those out for you. So here are some sample questions. So the first question here is how many kilograms are in a kiloton? And first we need to go back to our multiples. So let's see, question 1, if a gram is of the order of 1, then a kilogram, my pen out, so let's say a kilogram is 10 to the 3, that's 1,000 grams. A ton is 1,000 kilograms. So that's 10 to the 6 grams, and a kiloton is 1,000 tons. Kilo was 1,000 equals 10 to the 9 grams. And so if we want to say how many kilograms in a kiloton, so basically 1 kiloton equals how many kilograms? So a kiloton is 10 to the 9. That 10 to the 9 grams equals how many? 10 to the 3 grams. So the answer equals 10 to the 9 minus 3 equals 10 to the 6 grams. So equals 1 million. So that's your answer for question 1. So there's 1 million kilograms in a kiloton. So next question, how many terajoules are in a kilojoule? And this is just submultiples. So if you'll remember from the lectures, this memory for how to do these calculations. So start with kilo, mega, giga, tera, and after that is peta. So kilojoule equals 10 to the 3 joules, mega equals 10 to the 6 joules, a gigajoule equals 10 to the 9, and a terajoule equals 10 to the 12 joules. And of course that applies for every unit, not just joules. So the question is how many terajoules are in a kilojoule. So tera is 10 to the 12. And kilojoule is 10 to the 3. So we've got how many 10 to the 12s equals 10 to the 3. So equals 10 to the 3 minus 12 equals 10 to the minus 9 equals 1 billionth. Basically 10 to the minus 9 is 1 billionth. And the next question is how many gigajoules in, how many terajoules in a kiloton of oil equivalent. So we go to our conversion table here, and this is given in different units. So it's 41.868 gigajoules per TOE. So let's see. So it's 41.868 gigajoules per TOE, and that's the same as if we go up the multiples, a gigajoule, and multiply that by 1,000 terajoules per kTOE. So that's the same. So the answer is the same. There are 41.868 terajoules per kTOE, and it would be the same if we wanted a megajoule per kilogram of oil equivalent. 41.868. And the next question, how many kTOE in a gigawatt hour? We can use the same rationale. So if we're going from TOE to gigawatt hour here, we multiply by 0.86, and that's the same answer here, 0.86. So the next question will maybe illustrate why we're doing all this, and it gets a bit more interesting. So in 2017, Ireland's primary energy requirement was 14.473 kilotons of oil equivalent. What was the demand in kilowatt hours per person per day? So if we can bring that down, that number down to something more manageable. So I'd encourage you to try this calculation yourself based on the previous conversions. What you need to know is that there were about 4.8 million people in Ireland in 2017. And so from the 2017 energy balance, this was the total energy requirement. We can use the unit converter to see that this 14.473 is about 14.5 million tons of oil equivalent. That's equal to 168 terawatt hours. If we divide that by 365, we get to 460 gigawatt hours per day. Divide that by the number of people, 4.8 million, we get to about 100 kilowatt hours per person per day. So that's pretty interesting. So in the last quiz, we saw that 1 kilowatt hour kettle boiling for 1 hour is 1 kilowatt hour. So we use the equivalent of each day of a kettle boiling for 100 hours. Or you could also see maybe like a 10 watt light bulb. So 100 10 watt light bulbs burning for 100 hours a day to give you a sense of that. Next question I have is to compare the energy consumption from driving and cycling. So one of the reasons that we need to be used to these energy unit conversions is to be able to compare different forms of energy use. So let's say I have a 10-kilometer commute to work. When I cycle, my Fitbit or my bike computer says I burn around 250 calories. My car is old, and in a city, its rated fuel consumption is about 10 litres of diesel per 100 kilometres. How much more energy does the car burn than cycling? Again, I encourage you to pause the video and try to think about how you'd do this yourself. So cycling, 1 calorie is 4.18 joules. So 250 kilocalories, because of course when we talk about calories in the normal sense, that is actually kilocalories, is 250 times 4.8 kilojoules. So that's about 1 megajoule I'm burning from cycling, 1 million joules of energy I'm burning from my own chemical energy in my body. In driving, we need a different type of conversion. So 10 litres per 100 kilometers. So I use 1 litre of petrol for the commute. How much energy is in that? The petrol energy density is about 44,800 kilojoules per kilogram. The density of petrol is about 700 kilograms per cubic meter. So that's 700 grams per litre. If we divide by 1,000, 700 grams per litre. Water is 1 kilogram per litre. So petrol is less dense than water. There's 1,000 litres per meter cubed. So 1 litre of petrol, we can calculate the energy in this, 44.8 megajoules per kilo times the density times this conversion between meters cubed and litre. Check all the units that they cancel off. So we get 31.36 megajoules per litre. So we get more than 30 times the chemical energy is burned from driving, from cycling. And that's not surprising, because when you're driving, you're also carrying around a ton of metal with you, a lot of unnecessary seats, pushing loads of air out of your way. And cycling is really one of the most efficient, it is the most efficient form of transport that we've ever invented. It's really miraculous. Next question, question 7, is to give you a sense of the difference again between energy and power. So a couple of you thought watts were an energy unit, and I'd encourage you to really reinforce the difference between power and energy, as this is something that will come up not just in this module but in your whole life. And if you understand this, it will be one of those things that's clarified. So first of all, what's the wattage of a human body? That's a strange sort of question. You know, a light bulb or an appliance has a wattage, but that basically means what is the energy production or consumption of the human metabolism over time. So we, in other words, when we're just resting, our basal metabolism is around 2,000 kilocalories per day. So we can basically convert this 2,000 kilocalories per day in terms of how much we consume without doing any extra work. 1 day is 86,400 seconds, 24 hours a day, times 60 minutes per hour, times 60 seconds per minute. So 86,400 seconds. 1 calorie is 4.2 joules, and 1 watt is 1 joule per second. You know, if you know all those things now, can you go and figure that out? What's the wattage of the human body? So we've got 2,000 kilocalories a day, 2,000 times 4.2 joules, kilojoules per day. Divide that by the number of seconds. So you get 100 joules per second equals around 100 watts. So remember, 1 watt is at 1 joule per second. So we get, so the human body is doing no work is equivalent to the heat of around 100 watts. That's the equivalent of an old incandescent bulb in the middle of the room. That's remarkable that, you know, the human body and everything that we do runs just on that kind of heat that comes from a bulb. The last question for today again, is looking into this energy equivalence between oil and how much work a person can do. So it's said that the amount of energy in 2 teaspoons of oil is equivalent to the amount of work done by a person in a day. Can you imagine just 2 teaspoons of crude oil? So is that correct? We're looking here for really orders of magnitude, not exact numbers, you know, numbers of decimal places. If you think, how can you calculate how much work a person does in a day? You can look at say Tour de France cyclists and say that they can do, you know, at the max sprinting speed, they can do a few hundred watts, say 400, 500 watts sustained energy over you know, a couple of minutes. A good cyclist cycling, you know, in a race can produce maybe 200 watts over a few hours, but a normal person just working, doing physical labor can maybe do 60 watts of power over maybe 4 hours per day. So that's someone really laboring, maybe not a very fit person. So you're looking at the equivalence between 60 watts over 4 hours and 2 teaspoons of oil. Diesel oil has the energy content of about 42 megajoules per kilogram. And we can assume, just let's forget about the density issue at the moment. Let's just assume that 1 litre of oil weighs a kilo, and estimate that 2 teaspoons are equal to 1/50th of the litre. Now, can you take all these facts and see is the amount of energy that can be done, that can be performed by a person under these conditions equal to 2 teaspoons of diesel oil. So here's the calculation. So one person working at 60 watts for 4 hours, that's 240 watt hours. We want to get that into seconds to get to joules. In an hour, there's 3,600 seconds. Multiply that to get watt seconds. So 860 kilowatt seconds. Remember, 1 watt second is a joule. So we have 860 kilojoules from someone's daily work. Remember, power multiplied by time equals energy. And this is on top of the 100 watts produced by the body as heat that we calculated in the last question. So the additional power required requires additional food. So we estimate that the 2 teaspoons are equal to 1/50th of a litre. So we can then calculate that 1 litre of oil contains 42 megajoules, and 2 teaspoons is 1/50th of a litre, which is 840 kilojoules. So this is 860 from a person and 840 from 2 teaspoons of oil. So the comparison was correct. And I think that, again, illustrates the huge amount of energy that we're unlocking when we burn fuels like oil. Okay, I'll post a few other sample questions and answers, and also I'll post some sources, websites and readings that you can do to practice different questions like this on your own as well.